Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part number 5, we will discuss about lift and drag. So we will start with the introduction of the lift and also drag force in turbomachinery. Okay, now we start with we discuss about the different type of streamlines in term of its effects on the lift and also drag value. Okay, so before we discuss in detail about the streamline, so we need to know about the meaning of angle of attack alpha or AOA. So this figure shows a single blade profile, and the angle of attack in terms of definition is the angle between chord line and also the inlet fluid flow velocity vector C1. So this is the angle of attack, which is represented by alpha symbol. And so we'll look the difference between the streamline by using simplified schematic diagram and also the actual result they obtain from the smoke streamline for the wind tunnel investigation. And we will look the value in terms of what are the effect of this different type of streamline to the CL lift coefficient value and also drag coefficient value CD. So we need to refer the graph for CL, CD versus angle of attack. So this graph will show you in terms of CL profile, lift coefficient profile, that represented by green colored line, and also CD profile, drag coefficient line, that represented by red color line. Okay, for the first case, for the first condition, so we have alpha equal to 0 degree, where this angle actually based on the horizontal plane, which is equal to the chord line condition. So when alpha equal to 0, this condition means that the fluid flow direction will be parallel to the chord line or parallel to the horizontal plane. Okay, so we'll have at the trailing edge of the blade, so we'll have a region that represent by the region with blue colored line, and the region represent or call the region that will have I call turbulent wake, turbulent vorticity, turbulent flow, and so on. And the yellow point represent the separation point. The point refer to the starting point of the region when the fluid flow detached from the upper surface of the blade. Okay, so the second photo shows the actual result that obtained from the wind tunnel investigation. So the solid white line actually is the smoke streamline, represent the laminar flow condition. However, the area that have what called turbulent wake region actually represent by this region that what call the region between the two yellow colored line. So in the region we will not have the solid line because the smoke line disperse in this region due to the turbulent wake formation inside the region. Okay, so if we refer to the CLCD graph, so we will have the value of CL slightly higher than the value of CD at 0 degree angle of attack. Okay, for the second condition, we try to increase slightly increase the value of alpha to 5 degree, and we can see that the turbulent wake region or turbulent region that represent by two blue color line, and for this condition we can see that the separation point moves slightly forward on the surface of the upper surface of the blade. Okay, we can see clearly from the actual photo the change of the separation region or turbulent wake region. And if you look at 5 degree at the CL/CD versus alpha graph, so the value of CL increased drastically. However, the value of CD, drag coefficient, increased slightly increased. Okay, the third case or the third condition, so we increase alpha angle of attack up to 16 degree. So at this point you can see that the area of turbulent wake or separation increase for this case, and the separation point jump forward at the upper surface of the blade. Okay, so you can see clearly the separation point jump forward in the actual photo of the wind tunnel result. Okay, if you look to the graph, at this point we will have maximum value of CL. Okay, and also at this point we will have the value of CD increase drastically if we compare to the previous condition of alpha angle of attack equal to 5 degree. Okay. Okay. So you need to remember that the value of alpha at maximum lift condition is different for other type of blade profile. So this value alpha equal to 16 will give you maximum lift just for this example of blade profile. So if we use different type of blade profile, so we will get different value of angle of attack that will give you maximum lift condition. Okay, so you need to remember that. Okay, so after this condition, after the maximum lift condition, we will get the condition where the value of CL will start to reduce, but at the same time the value of CD still increasing. Okay, so this condition, because this condition is not good for the turbomachine operation, so that's why the point where we consider as the starting point of the reduction of lift value, so we consider as the critical condition. So alpha equal to 16 degree for this case is referred as the critical condition or the critical angle of attack, and sometimes we call stall angle. So stall angle, later on we'll explain in detail what the meaning of stall phenomena and so on. Okay, next, the last condition, we increase the value of angle of attack equal to 20 degrees Celsius, where this value represent the condition where the angle of attack higher than the angle of attack at the critical condition. So at this point we can see that separated flow region expand, and this region will reduce lift. This is one of the reason why the lift coefficient reduce in the graph. And we will have large turbulent wake in the region of the separation, and this is one of the main reason why the value of CL or lift force reduce, and also this condition will cause large pressure drag during the condition. Okay, so we can see in the actual photo where the separated flow region increase drastically when we increase the value of angle of attack greater than the value of angle of attack at the critical condition. Okay, so you can see that if you refer to the graph CL over CD versus alpha, the CL value for the last condition will reduce. However, the drag coefficient value still keep increasing. So this condition is not good for the turbo machinery application. Okay, the effect of lift and drag. Okay, this figure shows the what I call the blade condition for different angle of attack, and also the effect of angle of attack to the separation flow on the upper surface of the blade surface. Okay, so these figures or this schematic diagram we already discussed in previous slide, and also we describe in terms of CL and also CD value by using CL CD versus alpha graph. Okay, instead of CL CD, we also can use the graph or the profile for CL over CD to describe the change of lift and also drag. And so we can use this graph or this curve to show the effect of angle of attack to the change of lift and also drag value for the blade profile. Okay, so the highest point for L over D curve represent the optimum point, where this point normally we refer during the design process, where we need to choose this point in order to get the what I call the highest CL value with what I call with the acceptable value of CD, drag coefficient value. And for this point we consider numbers of safety factor in order to prevent the condition from enter the store region condition, where the region that we will have a reduction of CL drastically if we choose the angle of attack. Okay, as I mentioned before, for the case number 3, where angle of attack equal to 16 degree, we consider the angle for this condition as critical angle of attack, because after if we increase the angle of attack greater than this critical angle of attack, so we will get the condition where the value of CL will be reduced if we keep increasing the value of alpha, and at the same time the value of drag coefficient still keep increasing, and this condition is not good for the operation of the turbomachine. Okay, so the highest point of the CL curve we will represent the critical angle of attack point. Okay, so the region where we have CL reduction, we consider that the region as the stall region. Okay, so this stall region will include the case for case number 3 and also case number 4, where the angle of attack equals 16 degree and also angle of attack 20 degree. Okay, so the figure shows the actual separation region. So the photo we obtain the figure from the actual wind tunnel result, so we can see that clearly where is the location of separation flow, where we can see the area where we have a lot of turbulent features in the region. So the region we will consider as the separation region. So we need to prevent in any turbomachinery process operation, we need to prevent this kind of separation flow from happen. Okay, so the blue region in the graph of CL, CD versus alpha is the region where the angle of attack are below than critical angle of attack. And normally in terms of flow pattern during this region, the flow pattern of the fluid surrounding the blade blade profile is normally dominant by attached flow. However, in store region, the dominant flow type is the separated flow type, where we have in terms of separation region will be greater in this store region. Okay, what is the meaning of stall phenomena or stall process? Stall phenomena actually the phenomena where we will have the reduction in the lift coefficient generated by an aerofoil or blade profile as angle of attack increase. So that's the basics definition of stall phenomena. Okay, so this stall phenomena will cause slowing of the fluid in the boundary layer. So this effect we already discussed when we discussed about the blade profile losses, where we can see clearly that the velocity of V1, V2, V3, where we have the reduction of fluid velocity, and sometimes the flow will be reversed, and also sometimes the flow will stop during the process due to the stall phenomena. And the reverse flow during the process surrounding the blade profile will cause different type of blade losses. The second effect of the stall phenomena is called loss of pressure rise and or the increase in total pressure loss. So we need to differentiate between the pressure loss and also the pressure rise. So I already mentioned about the difference of these two type of pressure. So if you look at HS diagram, before this we will discuss about the pressure difference in a compressor. So if we neglect what we call most of the blade losses, we will get the optimum pressure difference, which is referred to P2 minus P1. So P2 minus P1 refer to the pressure rise. However, due to the blade losses, so we will get what we call the actual pressure difference P2 prime minus P1. So P2 prime minus P1 refer to the pressure rise after we consider the blade losses. And the difference between P2 and so P2 prime is represent the value of delta P naught, the total pressure loss. Okay, however, if we consider the condition enter the stall region where the stalling phenomena occur, so we will get more reduction in terms of pressure rise. So our new pressure rise is P2 double prime minus P1, and we will have higher value of total pressure loss where delta P naught increase represented by P2 minus P2 double prime. Okay, so loss pressure rise delta P for this stalling phenomena case refer to P2 double prime minus P1. Okay, what is the solution to prevent the stall phenomena from occur during the operation? First, we need to maintaining below a certain limiting value. Okay, so we need to consider, as we discussed before, the optimum value of L over D, and also so we need to very focus on the value of critical angle of attack for certain blade profile. So we need to determine this value in order to prevent the condition of turbomachine operation from entering the stall region. So if the condition enter the stall region, so we will have lower efficiency of a turbomachine. Okay, now let us look at an example of the effect of lift and drag effect on an aircraft wing. So before that, let us discuss about the effect of separation to the lift force. Okay, so the figure shows the attached flow condition for the aircraft wing. So the yellow color line represent the upper streamline of the aircraft wing, where according to the Bernoulli equation, fluid with high velocity will produce low pressure condition. And the lower streamline that represented by the blue color line will have low velocity with high pressure condition. So this a different called fluid condition is due to the shape of the airfoil profile. Okay, so now due to the pressure difference between the upper pressure and so lower pressure, so we'll have pressure difference delta P, and this delta P value is important because this value will determine the value of lift force. Okay, so delta P will produce lift force, so we need to have for aircraft wing higher value of lift force in order to lift the aircraft wing upward. Okay, now if we consider separated flow condition, okay, as shown in the figures, so this condition will occur if we increase the angle of attack. So we'll get the worst separated condition if the angle of attack is exceed the value of critical angle of attack. So now upper streamline will experience the turbulent flow or separation flow as shown by the yellow color line. And due to this type of separation, so we will have lower velocity with higher pressure condition. And if you compare to the attached flow condition, for the upper streamline will have higher value of pressure condition if you compare to the attached flow condition. And then if in terms of pressure, if you compare with the lower streamline, we will have delta P, pressure difference between the pressure at the upper surface and the lower surface of the aircraft wing. So we'll get lower pressure difference if you compare to the attached flow condition. So now the lower delta P or the lower pressure difference will cause lower value of lift force. Okay, so we'll have reduction of lift force. So we need to prevent the separated flow condition from occur to the aircraft wing. So in order to explain, to discuss about the example, the effect of lift and drag force to the aircraft wing, we need to refer to the CL, CD, L over D versus alpha graph. Okay, for example, we have an aircraft and the angle of attack of the aircraft wing is alpha equal to 0, where the direction of wind is parallel to the chord line of the aircraft wing. Okay, so due to the pressure difference, so we'll have specific certain value of effective lift force, so that the aircraft will fly at certain height, let's say 2000 feet. So what happens if we increase the value of alpha up to 5 degree? So we'll get higher value of L over D. Okay, so for this case we'll have greater value of effective lift force, and the aircraft will fly at higher position, let's say 30,000 feet. Okay, now we increase the value of alpha to 16 degree, where at this point we will have, in terms of L over D value, the value of L over D decrease. Although at that point, at the angle of attack, DCL is maximum. However, at the same time, the value of CD is higher. So we have lower value of effective lift force occur at that condition. Okay, so at alpha equals 16, so probably we'll get lower effective lift force. Then in terms of height of the aircraft, we'll get lower height, let's say at 25,000 feet, which is lower than the height if you compare to the condition of angle of attack at 5 degree. Okay, now when we change the angle of attack at 20 degree, so the condition of the airfoil of the aircraft wing will enter the stall region, where more separated region will occur on the aircraft wing surface, So we'll have call reduction of lift coefficient during the condition with higher value of drag coefficient. So due to the separation flow that occur on the surface of the aircraft wing, so the aircraft will fly at lower height, which is at 15,000 feet. So this condition occur due to the more separation occur, minimum value of lift force and higher value of drag force. Okay, however, in actual condition, we cannot change in the example, we change the whole position of the aircraft wing in order to obtain specific value of angle of attack. However, in actual condition, it is not practical to change the position of the whole aircraft wing in order to obtain certain value of angle of attack. Okay, the more practical approach is by using a mechanical component that we call aileron that are located at the back of the airfoil or aircraft wing, that represented by a green color component. By adjusting the position of the aileron, we will have different position of chord line with different angle of attack value. For example, we have the position of aileron that produce angle of attack equal to 0. The second condition, when we change the position of aileron, we'll get a different condition of chord line with angle of attack 5 degree. Okay, so we change again the position of aileron, we will change the position of the chord line, and we will get different value of alpha angle of attack. Let's say at this condition alpha equal to 16 degree. For the second example, we try to relate the example of aircraft wing to the turbine blade rotor. Okay, you want to know what is the effect of lift and drag to the turbine blade rotor. So we will use the same concept. Okay, so this is the what I call the photo of the gas turbine engine, and this photo shows the what I call the arrangement of the blade on the turbine rotor. Okay, so we will use the same concept of attached flow and also separated flow, where we need to have a higher value of lift force in order to the turbine rotor rotate with the high speed, and we need to prevent the separated flow condition, because this separated flow condition will reduce lift force, thus will reduce also the rotational speed of the turbine rotor. Okay, again we need to refer to CL, CD, L over D versus alpha graph in order to explain the change of the effect of the lift and drag to the change of the angle of attack. Okay, so the figure shows the arrangement of the turbine blade on the turbine rotor. Okay, let's say we set the angle of attack at 0 degree. So we have certain value of L over D. So the difference in terms of CL and also CD only with very small difference. So the schematic diagram shows the arrangement of identical turbine blade on the turbine rotor. So now the fluid enter the turbine blade rotor, and the angle will be equal to 0 degree. So the fluid direction is perpendicular to the fluid direction is parallel to the chord line of the turbine blade. So if you refer to the value of L over D, at this condition we will have this effective value of lift force. So due to this lift force, the rotor will rotate at specific specific rotational speed, let's say at 1000 rpm. So now we increase the angle of attack alpha equal to 5 degree. Okay, the fluid flow through the turbine rotor. So the value of, we will have higher value of L over D. So by referring to the value of L over D that we obtain for 5 degree, so we will have higher value of rotational speed, let's say at 2500 rpm. Okay, now we increase the what I call the angle of attack equal to critical angle of attack, which is 16 degree. Okay, so at this point, at this condition, we'll have lower value of L over D if you compare to the previous condition of alpha equal to 5 degree. Okay, so for this condition, we will have lower value of effective lift force. Although at this point we have maximum CL value, but at the same time we have higher value of CD, drag coefficient. So if you compare to the previous condition, alpha equal to 5 degree, at alpha equal to 16 degree, we will have lower effective lift force. So for this condition, we will get lower rotational speed, let's say at 1500 rpm. When we increase further the value of alpha, where the value of alpha equal to 20 degrees Celsius, and this angle is greater than the angle of alpha at critical condition. So now at this condition, CL reduce and CD we will have higher value. So probably at this condition we will have more separated flow region that cause a lot of losses. Okay, so due to the condition, we will have more reduction of effective lift force to the condition. So we will have lower rotational speed, let's say at 500 rpm. This is because the condition already entered the stall region of the turbine blade profile. So that's why we need to prevent what I call the condition from entering the stall region, and also we need to prevent the separated flow from happen during the turbomachine operation. Okay, because the condition will reduce the efficiency of the turbine. Okay, before we start with the basic equation, so I have a correction. So in the previous slide I mentioned about the alpha equal to 20 degrees Celsius. So that's a mistake that I have done. So alpha equal to 20 degree, not 20 degrees Celsius. Okay, next we will learn about the basic equation for lift and drag. So for this session, for this subtopic, we will derive the equation for lift and also drag force. Okay, for derivation of equation, we will start with derivation of lift equation. Okay, we look at this schematic diagram. So this schematic diagram actually is a schematic diagram for the blade profile that consists of inlet velocity vector C1 and also outlet velocity vector C2, and we can create velocity diagram for both C1 and also C2. So we'll get this kind of velocity diagram, combination of velocity diagram that we have learned in previous lecture, and the velocity diagram also include the velocity diagram for CM. So we have D vector, which is the drag force vector, where the direction is parallel to CM vector with reverse direction. And we have L vector, which is referred to lift force vector, and the direction is perpendicular to CM vector. Okay, so we also have Y force vector and also X force vector. So the angle between y force vector and also lift force vector equal to alpha m. So if we refer to the vector principle, so we can extract all the vectors in this schematic diagram and draw the vector diagram as shown in the figure. Okay, so redraw the vector diagram. Okay, by referring to the diagram of vector, if we look into detail, we can divide L vector into L1 and also L2, which means L vector equal to L1 plus L2. For vector y, we can divide into two, part A, part number 1 A, and also part number 2 y minus A. So from the vector diagram, we can extract two type of triangle: red color triangle with angle alpha m. So we have first line L1, second line A, and the third line is x in terms of distance. Triangle number 2, green color triangle with same angle alpha m. So we have L2 line, y minus a line, and also d line in terms of distance. Okay, implement trigonometry principle to both triangle. So we'll get first equation, L1 equal to x divided by sine alpha m. Equation number 2, L2 equal to bracket y minus a multiplied by cos alpha m. Equation number 3, a equal to L1 multiplied by cos alpha m. Substitute equation number 3 into equation number 2. So we get equation for L2 equal to y multiplied by cos alpha m minus L1 cos square alpha m, which is referred as equation number 4. Substitute equation number 1 into equation number 4. So we'll get new L2 equation, L2 equal to y cos alpha m minus x cos square alpha m divided by sine alpha m, which is referred as equation number 5. Add equation number 1 and also equation number 5. So we'll get the equation for L. So this is the general equation for lift force, where we have L equal to x sine alpha m plus y cos alpha m, which is referred as equation number 6. Okay, in order to include the term of total pressure loss into the lift force equation, so we need to use basic equation for total pressure loss, which is referred as equation number 7. Substitute equation number 7 into equation number 6 and use trigonometric rules. So you'll get new arrangement for the L equation. L equal to bracket y tangent alpha m minus s delta p naught multiplied by sine alpha m plus y cos alpha m. Apply the trigonometry rules, so you will get L equal to y second alpha m minus s delta p naught sine alpha m, which is referred as equation number 8. Okay, so now implement y force equation, which is represented by equation number 9. Substitute equation number 9 into equation number 8. So you will get the final equation for lift force that include the total pressure loss terms into the equation, where L equal to rho scx square multiplied by bracket tangent alpha 1 minus tangent alpha 2 multiplied by second alpha m minus s delta p naught sine alpha m, which is represented by equation number 10. Okay, by using the same diagram as the derivation for the lift equation, in terms of schematic diagram, vector diagram, velocity diagram, and also the triangle diagrams. So by implementing the trigonometry principle to both triangle, so you'll get what we call the equation number 1 for drag force, where D equal to bracket Y minus A sine alpha M. Equation number 2, A equal to L1 cos alpha M. Equation number 3, L1 equal to X divided by sine alpha M. Substitute equation number 3 and 2 into equation number 1. So we'll get the general equation for drag force. D equal to Y sine alpha M minus X cos alpha M, which is represented by equation number 4. So in order to include the total pressure loss equation, so we need to use the basic equation for the total pressure loss that refer to the equation number 5. Substitute equation number 5 into equation number 4, so we'll get the final equation for drag force, where D equal to cos alpha M multiplied by bracket Y tangent alpha M minus X, also equal to S delta P naught cos alpha M, stated by equation number 6. Okay, example 2.4. Figure shows force diagram consists of X direction force, Y direction force, lift force and drag force. Alpha M in the figure refer to mean flow velocity angle. Using the figure, prove that equation of lift force and drag force are as stated below. L equal to X sin alpha M plus Y cos alpha M, and D equal to Y sin alpha M minus X cos alpha M. So try to work out try to work out with the example 2.4. So by referring to the figure, you need to derive the equation for L force and also drag force as stated in the example. Okay, in order to test your understanding, please answer the question. By referring to the figure provided below, answer the question. First, in order to obtain the best design for a turbomachine blades, which point do we need to consider for L over D, CL and also CD? Question number 2, which point of CL and CD are referred to when the angle of attack is negative? Number 3, point for L over D where separated flow is dominant. Number 4, maximum point for CD that still can be considered. So you need to answer the question. You have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue also is given in the link. Okay, so this is the figure that refer to the question. So you need to choose the suitable point according to the question given.